CS6963, summer 2013, reporting on my final project, which is LANMap, which is a Python utility for reporting on local network hosts from a PCAP file. So I'm going to give you a quick overview of my project and my approach, and then I'm going to give a demo of the tool running and then return to the presentation while the tool runs, and then we can go through the output a little bit. So as an introduction, as I said, this is a tool that reads a PCAP file and reports on the hosts and devices found on the local network, local to the capture. And this is currently based on ARP and IP traffic primarily. It only works on IPv4, and future work could add additional information on routers and services available on the local network using DHCP, SSDP, other discovery protocols. It is written in Python 2, and it is licensed under the MIT license. The only dependency outside of the standard Python libraries and SQLite, only dependency is the dpacket packet processing library, and that is for reading the PCAP file and handling the individual packets. So my motivation for doing this is from the Nitroba case that we had as a homework assignment. I found that I had to use a lot of different tools just to extract and organize information about the local network. I had to use Wireshark, TCP dump, and then a bunch of bash tools, VI, sort, unique, grep, and cut, just to kind of organize everything into a simple table that said these are the local hosts and the devices and IPs that were associated. It seemed overly complicated and labor intensive, so definitely a problem worth solving, and with this assignment I attempted to do that. So here's how you run the utility. It's just a simple Python script. You can make it executable and run it on the command line. It takes only a very few arguments. The main one is the actual PCAP file. That is required. Everything else is optional. If you care to, you can specify a path to an output file, and it will write the output report to that location. You can also specify that you want to keep the database that it saves everything to, and if you do that, it will write it to the same directory as your output file. I do not recommend keeping the database. When you use SQLite with an on-disk file, it is very slow. There are probably some performance parameters I can tune, but my experience was that this was about 6 times slower than running it with just an in-memory database. So if you actually want to use the tool, run it in memory. If you want to look at the database, then you can keep the database. It's primarily useful for debugging. So now I'm going to go and run the utility. I've extracted 40,000 packets from the Nitroba case, and we'll run it. So just a quick orientation here. Let's see where we are. I'm in my project folder. Here's our files. This is the presentation we're discussing right now. Here's the script itself. Here's a little README file. And this has just some overview information and instructions, dependencies, compiling and installation, and usage and license. Okay, so if we want to see how to run it, we just do this. It's the same information we just saw. Okay, so let's actually run it. We're going to run on 40,000. And you saw that that was in my captures folder. And we are not going to keep the database. So this should take a couple minutes to run. Okay, here it is. Opening the file, reading the packets. This could take a few minutes, and it will. Okay, back to our presentation. So how do I do this? First thing I do is I set up a database. And as I said, definitely you want to make that an in-memory database. Then I attach the PCAP file using dpacket and read the packets sequentially. I don't use any kind of filtering. dpacket doesn't support it, and in addition, I want to read all the packets because I want to be able to descend through the hierarchies and collect information from each of the different kinds of packets, so I'm not going to filter them. For each packet, I construct the dpacket representation. Well, dpacket actually does that for me. Then I descend into that packet hierarchy and extract information, as I said. Currently I'm only looking at ARP, IP, and HTTP request packets. The others I identify, but I don't actually make any use of them right now. So I save the packet details to the database, and then after all the packets are in the database, I query the database for local hosts based on the ARP activity, and for each local host then I aggregate the data by IP and by device, and so then I write out a report. So a quick note on perspective. When you're looking at the local network, there are two ways to look at it. You can look at it by host, IP address, which is how the traffic is routed from one computer to another. If you're visiting a website or something, that's by IP. But that IP can also be assigned to another machine. So if you want to know who was doing something on a network, you need to look at the machine itself. The MAC is associated with the machine unless there's some MAC spoofing, which is possible, but let's not address that right now. So this tool is capturing data on both IP and MAC, and I do this using what I call the session approach. You'll see there are many, many sessions, and this is because addresses can be reused. A device can drop off and an address can be assigned or taken by another device. And then also traffic routing. So anything going through a network device, a router, a gateway, modem, gets the MAC of that device, but then the IP address of the destination beyond it where the traffic is going. And so what I do is I report from the host perspective by IP, and then I show all of the MAC devices associated with that IP. That's just the approach that I took. Okay, so the protocols that I used, I look at ARP. ARP is kind of somewhere between layer 2 and 3. It lets hosts determine the Ethernet address of other IP hosts on the same network. And so it's a good way to figure out who is local and who is not local. Hosts request a MAC for a given IP and then they wait for a response. They can also just announce their location in what's called a gratuitous ARP. And so for our purposes, any host that's sending an ARP packet, whether it's a request or a reply, is alive, is on the local network, and is active. So we save that information, create sort of an ARP session in the database associating the MAC and the IP, and we update the count of how many ARPs there have been for this pairing and the timestamp. Okay, IP, Internet Protocol traffic, this is the bulk of the traffic on the network. Most things are traveling over IP, whether it's TCP or UDP on top of IP. This is solidly a layer 3 protocol, and it's a true sign of activity. So while some hosts may respond to ARP, they don't actually have any traffic going on, they're just there. And for our purpose, any host that's sending an IP packet, whether it's a request or a reply, is alive and active. So we save the MAC and the IP of the database, we update the counts and the timestamp. We also track packets that are received at hosts, but I don't update the timestamps because it's possible somebody's sending traffic to a host that isn't actually active. So the traffic might be on the network, but nobody's there to receive it. So we only care about the times that somebody sent something. That's when we know they're actually there and active. Other protocols, right now I'm looking at HTTP requests to extract the user agent. User agent is the string that your browser sends out to tell your servers what kind of device you are. It doesn't have to be accurate, but if somebody hasn't modified it, it contains some useful information about the operating system and the client software that they're using, including names and products and versions. So it could be helpful for developing a profile on the host system. So I save the original string, and I also go out and use a web service to parse it, and I save the components into the database, and I update the count of requests. Some other protocols I looked at using were SSDP, which is a network service discovery protocol, and DHCP, which does not just dynamic IP address assignment, but also notification of network services. So through DHCP, you could be notified of your local mail server and name server and all kinds of services. So that could be useful if you're trying to build a profile about a local network. I didn't have time to include it, but it's definitely possible. Okay, and then how do we do the analysis? So first thing I do is I collect all of the address pairings from the IP session table for which there was ARP activity. So this is telling me who was a local host and what was their activity in the IP protocol realm. And this allows me to exclude anything that's a remote IP and only focus on the locals. And then for each local host pair of IP and MAC, I do an aggregation of all their traffic counts and volumes, session totals, and an activity span. And note that the activity span is the total time from the first time to the last time that this host was identified as active on the network. But as I said before, IP and MAC pairings can come and go and be overwritten. So the total span accounts for a lot of time that another device may have had the same IP or MAC address. Just saying the total time from start to end that it appeared, but it's not always active with that host and MAC pairing. And I also collect the number of hosts associated with a device, which is the inverse of the way I'm presenting it. So you'll see the information's in there kind of twice. Finally, for each device, I look up the MAC prefix to associate the manufacturer, and I use another web service for that, and it's a little bit flaky, so sometimes I get results, sometimes I don't. For each device, I also get the aggregation of all the user agent fields, and this allows me to report the most frequently reported OS company and family, along with the user agent software. And for the user agent, I report anything that had greater than 10% of the HTTP requests. For testing, I tested this against the Nitroba case and some captures that I set up and ran here on my home network. Nitroba is a pretty well studied case, so it was very useful to run against that, and then I could compare it to known results. So what's on the roadmap for this utility? Well, there's a lot more that we could do. This was just a small project within a class semester, but definitely more protocols, as I mentioned earlier. This only support for IPv4 right now, so IPv6 would be something to add, as well as DHCP and SSDP and others, as I said, for more information about the local network and services. Also better output. Right now it's just doing a plain text dump to a specified file, not very reusable. You're limited to the format that I provide. JSON or XML, some other kind of output form would be useful. In addition, maybe a graphic user interface or an actual graphic showing the visualization of the network. So those are some things. In addition, more testing, certainly more testing, more captures, more hosts, more protocols, unit testing. Performance, it's not the fastest thing. Definitely could use some optimization and database tuning. When you write and create and save the database, it takes a significant amount of time. Doing it in memory is pretty fast, but when you save out the database, it's slow. In addition, there's no recognition of broadcast addresses in there right now, so broadcast MAC addresses and IP addresses just show up as other addresses, and they get filtered out for the most part. But explicit recognition of them could help in overall mapping of the network. Okay, so let's go to the demo. I've just analyzed 40,000 packets from the Nitroba case. Doing the full Nitroba capture with it's about 95,000 packets with an in-memory database took me about 10 minutes. So it seemed a little bit long for this demo, so I just did 40,000, but there's still enough in there to see. So let's see if that's completed. And it has. So this is the very limited interface. Just tells you what you're reading, that you're reading the packets, that we found 40,000, and that the report has been written to this location. So if we look there, we should see it. There it is. And let's browse that report. Okay, so here's what's in the report. There's kind of a report summary. Just tells you, what you read, how much was in there, what was the earliest packet in the protocol, in the capture, what's the latest packet, what's the total time span, how many total hosts were observed. We got 8 local and 197 remote, and then how many devices? Well, that's by MAC address. So now what we do is we walk through the report. We can see each host and then the number of devices associated. And then for each device associated with a host, we get the MAC address, again the span of time that it was present, total number of packets, bytes and packets sent, bytes and packets received, local IP association. So you can see that for this device, two IPs are associated. So remember this 0031, we'll see it again later in its other association. No remote IP association, so this is definitely not any kind of a network device. Okay. Oops. So you can also see here our web service worked, and this device by its MAC address is associated with Apple. And that's all the information we got for this device. It didn't send any traffic, it sent very little traffic, so there's very little to report on it. Okay, 192.168.1.5 also didn't send very much traffic, also by Apple Computer. This is the only IP associated with this device. 192.168.164. Alright, so we sent a little bit more traffic, and we received some traffic, and we can see that this is by Hanhai Precision. I think that's also Foxconn. There were 24 HTTP requests, and so from the user agent information in those requests, we learn that this is probably an Apple computer, and the OS is Mac OS. And these are the only user agents reported. So Apple Pub Sub, I'm not sure what that is, and iTunes. Okay, keep going. Okay, so 192.168.1.254 has two devices associated with it. So we'll see what that looks like. Here's the first device address. And we can see that that is by Motorola, used to be Netopia, and so I think this is a router. We can see also that unlike the other hosts that we looked at who had 0 remote IP associations, this one has 19 remote IP associations. So that's traffic that is going to this device, to the MAC address of this device, but destined for an IP address outside of our local network. So that means that some local host is sending information to this host to go to an IP beyond the network. So this is probably a router or a modem or something. And the fact that it is by Netopia or Motorola seems to confirm that. Okay, but then that same IP later is associated with this MAC address, and an even larger number of remote IPs. So again, confirming that this is probably some sort of network device. And I think from the original Nitroba case, we learned that this is the airport router. Okay. And so here is another host, and again you can see there's local IP associations is 2, which means that this host has appeared somewhere else or will appear somewhere else already. Let's see where that is. Oh, there it is. So this IP, this MAC address was used here with this address, and then also with 15.1. And it did send some amount of traffic. Okay, now here's this 15.4, if you'll remember from the actual Nitroba case, this is the main machine that we focused our investigation on. And you can see, as you'll recall from the case, that it is an Apple computer, quite a bit of traffic to and from this machine. And by user agent analysis, we're getting a lot more information here. So again, Apple Computer, 1,800 web requests, Apple Computer, OS X. We can see that we got a little bit more information from some of the user agent packets, had a little bit more details, so we add those here. And then we got more on the actual browser user agents, Safari, Firefox, and their versions. So again, more helpful information. And here are some additional hosts and devices, and that's about it. So we'll do one more thing here. Let's do a quick run of the utility on a smaller set, and I'll show you what the database looks like, and then we will wrap it up. So I'm going to add the keep db argument, and that should take another couple minutes, and then we'll be done. So while that's running, I'll just touch one more time on some of the areas for expansion. There's a universe of protocols out there, and I really just focused on the major ones that would get me the information I would need to map the local network. And so this tool is rather limited right now. It can basically just provide that limited information I just showed you. We'd get a lot more out of it if we were getting some other protocols, other packets, and identifying additional network services. I'll just let that finish up for a minute. Actually, I think what I can do here is just show you a different database. My goal was just to run one and keep the data. Oh, there we go. So, okay, and there it is. That's what I wanted. Okay, so what I want is this database file. So what I've got here is a small open source utility for browsing SQLite databases. Let's open that up. And here's the database. So you can see in here the IP session table, and you can see there are, for those 5,000 packets, 1,200 sessions in here, so quite a few. And you can see a lot of them are nulls. A lot of the date stamps are nulls, which means that these were these are packets receiving data at a host that isn't in the table yet, so we insert those as nulls. And you can see there's just a lot of sessions, especially with this address right here, which we identified as a probable network device and has a lot of remote IPs associated. Here's the ARP session table. Much fewer in here. There are only a few local hosts, as you can see, and also a lot of bogus addresses, and these kind of get filtered out when we compare ARP against the IP tables. And if you recall, this network had no DHCP. It uses static IP address assignment. So this could be users just fat fingering addresses or stumbling around trying to find one that works on the network. And the final table is the HTTP requests, and since there wasn't a lot of traffic in that 5,000 packets, there's only a few things in here, but you can see I've got the full user agent string and then the parsed values that I got from the web service. So it was kind of interesting, useful for debugging. That about wraps it up. I hope that was interesting for you. Sorry for the little delay there while we ran. As I said, it's kind of slow to generate the database and save it. Much faster when it's running all in memory. Hope that's a useful utility. Maybe you'll have some interest in extending it, and please let me know if you have any questions. Thank you.